In the beginning, around 400 BC, there was pi.
Incorrect.
In the beginning, there was a place called Greece. In Greece, there was a man called Democritus. Now he happened to have a brain.
Like me.
With that brain, he created the particle theory of matter. He believed that every single thing in the universe has an indivisible particle called the atom.
Atom meaning indivisible in Greek.
Around the same time, there was another man who shall not be named.
His name is Aristotle.
He believed that matter is continuously divisible. You can cut it in half forever.
But neither of these men had actual experimental evidence.
Only a few years.
The 1700s is not just a few years later. It is in fact 2,100 years.
Anyways, a man called Dalton created three basic laws. The law of conservation of mass, law of definite proportions, and law of multiple proportions. The law of conservation of mass states that during chemical reactions, matter is not created nor destroyed, but is conserved.
In other words, aka more scientific words, for example, in photosynthesis, 6 CO2 plus 6 H2O plus light is equal to C6 H12O6 plus 6 O2. In the start, there is carbon dioxide and water. When light is introduced, the result is organic compounds and oxygen. And in both beginning and the end, there's the same amount of mass.
The law of definite proportions states that two of the same substances, for example salt, found in South Africa and salt found in Australia,
even if they have different masses,
will have the same proportions of elements. The law of multiple proportions states that two or more different compounds that have the same elements, the ratio of the elements in the compounds are related by a whole number.
For example, if there's a compound called Young's and a compound called Old's, and there was 3 carbons and 1 hydrogen in the Young's and 1 carbon and 3 hydrogens in the Old compound, the ratios are related by 9.
In 1803, Dalton proposed that each chemical element is composed of unique atoms that cannot be altered or destroyed by chemical means.
He also said that atoms can combine to form compounds.
Come on! Then in 1897, J.J. Thomson came up with a plum pudding model. Yum.
With the help of his cathode ray experiments, of course. Yeah.
Thomson noticed that the cathode was not losing mass, but rays were still being emitted. This meant that particles in the cathode rays were being replaced by electricity. Thomson also noticed that the rays were deflected by a magnet, and he concluded that rays were negatively charged. Since atoms are neutral, Thomson concluded that there must be a positive charge, so he proposed the plum pudding model, where positively and negatively charged particles were floating around freely, living happily ever after. Until 1909, Robert Milkman,
You mean Millikan?
did the oil drop experiment to figure out the measure of electric charge. Using charge equals attraction,
E over m equals charge of the electron.
Millikan figured out the mass of the droplets and was then able to calculate the mass of electrons. In the same year, Ernest Rutherford experimented by shooting alpha particles through a sheet of gold foil to a deflector screen. Unexpectedly, some of the alpha particles deflected back in ways that seemed impossible.
Since they happen, it's not impossible.
Stop, please. This led to Rutherford concluding that the positive charge of the atom must be concentrated in a small volume in the center. He then created the planetary model. The planetary model consists of a cloud of electrons surrounding a small compact nucleus. Finally, in 1932, Chicken Sandwich,
No, James Chadwick.
I was getting excited. He found that the planetary model is incorrect because the positive charges inside the nucleus would repel each other instead of staying in a small bundle. And also, the total mass of the atom did not match the mass of the electrons and protons. So by experimentation, he concluded that there were neutral forces.
Called neutrons.
They held the protons together, all happily ever after inside the nucleus.